my research question and the specific research direction I'm going for this week was the effect of different action space abstraction levels on RL policies. For a brief preliminary, basically supervised learning works with a data set, and what you're trying to do is train the model with parameters, and you're trying to minimize the loss. Reinforcement learning and unsupervised learning are quite different. You have a state that goes into an agent, and you predict an action in the state that maximizes the reward, which I define, which is typically defined like J here. So you have an action that goes into a policy, which outputs an action, and this specific part, we call that the action space, and this is designable. It's basically how you control your environment, and there can be different levels of abstraction space. And the abstraction level can, a good analogy is like this: drive to CSTU, that's really high level. And a more low level would be like drive forward 10 meters, turn left. So as you can see, that one's way more understandable than that one, and it's way more higher level. So my methodology is I set up, so for my policy, I'm using a Gaussian NLP, and I'm training with a very standard reinforcement learning technique called PPO. And the Gaussian NLP, all it is our model is predicting a mean, U, and a variance, and we're sampling an action from that. And my action spaces, I tested on the low level, which is basic torques, and the high level, which is a PD controller. And a PD controller is basically, you can think of it as a model that takes in a position. Say my arm moves to this position right here in XYZ. It takes that and it produces some torques that makes your arm move there. And this changes the action space and is more higher level. For the systems, I decided to test on the following system, which is decreasing in complexity, starting with a humanoid walking, a robot arm pushing, and a reacher to reach a specific point. And the metrics I'm testing for is the reward of the policy, as well as the entropy. The entropy is the proxy I'm using for the abstraction level, because if you think about it, a more higher level action space, it's more certain about how the action. So like say like the analogy before, drive to CSTU, you're more certain that that's what's gonna happen compared to say like move forward 10 and like turning. These are the systems I'm testing on. Reacher, which is that one, humanoid, which is in the middle, and pusher, which is there. And here are the results of here. As you can see, there is learning going on, and the first point I want to point out when I first saw this was reward. Reward design is extremely important. As you can see here, these are all quite messy, and they're not the best learning curves, but this is because I just used the standard reward and I didn't formally design the reward. This also points to another result I found, which is exploration. Exploration is also really important for learning, and as you can see here, there's like a lot of exploration going on, and subsequently from that, there's also a lot of local minimums, which I fell in during training. So exploration can help you get out of the local minimums, and I'd say that the local minimums from my results, I infer that it's mostly caused from reward hacking and having a poorly designed reward. The second point I want to make out is the abstraction level trends. Initially, one of my hypotheses was the abstraction level from higher to low. A higher abstraction level would perform better on a more higher complexity system like human, while a lower abstraction level would perform better on a more simpler system. As you can see from this trend, that's actually not the case here. The PD controller, which is more higher level, ended up performing worse here and ended up performing higher here. And this trend, I do not have a mechanistic explanation for this, and this would require more experimentation to find out why. And another thing you might notice is in the bar graph that shows the entropy for each of our action spaces, it actually shows that PD controller had a higher entropy, which means from this graph, the abstraction level of PD would actually be very low. However, in the standard industry and standard state of the art, it's very often stated that PD is a high level action space. So there are two possible explanations for this. One of them is there is another mechanism for her which would require more experimentation to find out why. And another one, which I say is more probable, is because entropy is not just great and in general for this metric, and that is because for different tasks like here, the action space, how broad it is, varies. So for Reacher, there are multiple ways you can get to that point, but for human, there is less of that. And that would that's a variable that would actually affect entropy. So the level of abstraction space is not the only variable that would be affecting it, which is why I say it could be a bit of an ill-defined metric. So the key takeaway here is the real journey was the reward models we made along the way. Reward modeling is extremely important for design. I have some visualizations of the truth. I have some visualizations here, and here it was hacking it like a lot. So basically the reward here was to survive longer. I thought that would make it walk. Instead, the model learned to go on its knees, as that would make the episode not terminate. And as you can see here, it's actually the same result, although it was able to walk a little bit. And as you can see here in the pusher here, it learned a really suboptimal policy to use the elbow to reach it. And you can see here that also it also reward hacked here by simply continuously trying to go around to touch the point, which is another suboptimal policy. And here, these two just hovered around. These two just hovered around our target point like this. And this would require a little bit more experimentation. Maybe there's another mechanistic. However, I'd say what is more probable is that's probably another suboptimal local minimum that it fell in. So one of the very main takeaways here is that the reward modeling is very important. So thank you for listening. The floor is open to questions if you have any.
Go ahead and pick. Focus on people who haven't asked questions already.
Not asked.
I think Eric hasn't, and also people from the 280 class.
Oh yeah.
What are the hyperparameters on this model?
Yes, that is one of the hyperparameters on the model. So for PPO, there's a lot of hyperparameters. I can pull up, but there's like a lot. I'd say that my learning rate for it was around 0.003.
You need to give exact values.
Yeah. Basically, my learning, it's basically I just use the very standard PPO like parameters for each, and I say that could possibly be one of the limitations to my methodology as well. Is different systems would have different hyperparameters, which would be another variable.
Okay. I was going to give Candy to
Jason.
So apology, like for the walker, we could like the walking one, just because it's so much more complex than the other two. How do you think you would like change your reward system for that specific like one?
So the reward system for Walker, instead of just having the reward being how long it would survive, in which it would fall into a local minimum like that, I would add a reward for a forward moving velocity, which would a forward moving velocity, which would encourage the model to actually move forward instead of just trying to reward hack and stand still like that to try to survive.
Let's do the last question. I'll give you my question.
Okay, one comment that you should also add a conditional balancing. That's gonna help you a lot for bipedal balance, like a maintaining balance is another condition that you should consider. And the other thing is, can you scroll back to your results here? You notice that between human, breacher, and pusher, there's an inversion in torque and PD reward. Can you explain what hypothesis might have for that?
An inversion?
Like human, breacher, and pusher, the rewards are inverted.
The rewards are,
Like the pattern, yeah, the shapes are all inverted, so in human, the rewards are, like the PD rewards below.
So the positive, the negative.
Yeah.
Yeah, so in Reacher and Pusher, the reward is designed so that it's the negative distance away from the goal. That's simply one of the standard designs they use in Reacher, which is why.
Are you asking why
why
red is
they're
on?
inverted.
So she's asking specifically, the torque is above PD in human, but is below PD in pusher. Why did they flip? Why is it not just that torque is always better or PD is always better?
So this was the exact research question which I was trying to answer, which was the different abstraction levels and how they train. So here, this would require a mechanistic experiment to explain why specifically for torque the low level it performed better here compared for the PD the high level it performed worse here and better there.
Cool. All right, thank you very much. Because we're running out of time,